Welcome to Sleepy Nature Facts. Somewhere outside, or somewhere in the quiet geography of your memory, there is a river. It may be a river you have seen, a river you have crossed, a river whose name you know because you grew up near it, or traveled beside it, or read about it, in the particular way that rivers appear in stories, as boundaries, as passages, as the things that separate one world from another and connect them at the same time. Or it may simply be a river you can imagine, wide and slow and moving through a landscape that has no name and no urgency, simply water following the oldest instruction it has ever received, which is the instruction of gravity, pulling it downward through whatever path the land has left available. That river has been following that path for a very long time. The Amazon River, which carries 1/5 of all the fresh water that flows in all the world's rivers combined, has been flowing eastward, toward the Atlantic Ocean, through the largest rainforest on Earth, for approximately 11 million years, which means that the path the Amazon is following tonight is a path that was established before the first human beings existed in any form, before the grasslands of Africa, where our ancestors evolved, had taken their current shape, before most of the species currently alive on Earth had yet appeared in the fossil record. The Nile, which flows northward through the world's largest desert to the Mediterranean Sea, in a direction that seems to defy the intuition that rivers should flow away from deserts rather than through them, has been flowing in roughly this direction for at least 5 million years, longer than the existence of the genus Homo, longer than the existence of most of the organisms visible in the Egyptian desert that the Nile crosses each day of its ancient and unchanging journey. Rivers are among the most continuous, most persistent, and most ancient features of the Earth's surface, older, in many cases, than the landscapes they flow through, older than the species that live in them, older than the civilizations that have built themselves on their banks and organized their entire cultural and agricultural and spiritual lives around the expectation of the river's presence and the reliability of its flow. But here is the thing about rivers that most people never fully absorb. The thing that changes the quality of attention you bring to any river you encounter once you have understood it. And that is where this night is going to begin. A river is not simply water moving through a landscape. It is a living archive, carrying in its current and its chemistry and its sediment and the biology of everything that lives within it, the recorded history of every event that has occurred in every square kilometer of the land it drains, going back not years or decades but millions of years, a continuous and self-updating record of the geological and biological and climatic history of an entire watershed, written not in stone or paper but in water, moving past you at whatever speed the gradient allows, carrying everything it knows toward the sea. Tonight, we are going to learn to read that archive, slowly, without any urgency at all. You do not need to stay awake for this reading because the river has been flowing for 11 million years, and it will continue flowing long after tonight. And the archive it carries is patient in the way that only something truly ancient can afford to be patient. It is not going anywhere. It is simply continuing, in the dark, in the current, in the quiet and unhurried way of water that has always known where it is going and has never needed to hurry to get there. Before we follow the river downstream into everything it knows and everything it carries, there is one thing we need to understand first, and it is the most counterintuitive and most quietly astonishing fact in the entire science of rivers. Where a river begins. Most people, if asked where a river begins, would point to something specific and visible. A spring emerging from the base of a hillside, a mountain lake draining through a narrow outlet, a glacier melting at its terminus and releasing a thin, cold stream that will become, over the miles that follow, something considerably larger, and considerably less thin and cold than its beginning suggested. And these answers are not wrong exactly, in the sense that springs and mountain lakes and glacial meltwater are all genuine contributors to the flow of the rivers they feed, genuine beginnings of the visible water that the river eventually carries. And the source of a great river, the specific geographical point at which the river's main stem can be traced back to its furthest upstream origin, is a real and meaningful concept in hydrology, even if, as we will discover, the precise location of many famous rivers' sources was disputed for decades or centuries before being definitively established. But the truly correct answer to the question of where a river begins is something that no visible spring or mountain lake or glacial terminus quite captures, because the truly correct answer is both simpler and much stranger than any of those things, and it requires a shift in the scale at which you are thinking about the river, from the scale of the visible channel and the visible water to the scale of the entire landscape that surrounds the river and feeds it, a scale so large that it is difficult to hold in the imagination all at once, but that, once held, reveals the river as something fundamentally different from what it appeared to be when you were only looking at the water in the channel. A river begins in the raindrop, not in any single raindrop, not the specific, identifiable drop of rain that falls on any particular leaf or any particular square meter of hillside and begins its journey toward the river channel. But in every raindrop that falls anywhere within the river's catchment, the entire area of land that drains toward the river's channel, every drop of precipitation that falls within this area already belonging, from the moment it leaves the cloud above it, to the river below, already committed to the river's flow by the simple fact of having fallen on the right side of the invisible line that separates the river's catchment from all the other catchments surrounding it. This invisible line is called the watershed, or the drainage divide, and it is one of the most consequential and least visible geographical features of the landscape, a boundary that exists not as any physical feature of the terrain, but simply as the line along which the gradient of the land surface changes direction, where the slope that drains toward one river system meets the slope that drains toward another, determined entirely by the topography of the land, by the precise configuration of ridges and valleys that the geological history of the landscape has produced. On one side of a watershed, every raindrop that falls is already on its way to one ocean. On the other side of the watershed, often within a few meters or even a few centimeters of the first raindrop, every raindrop that falls is already on its way to a different ocean, possibly on the other side of a continent. The continental divides, the great watershed boundaries that separate the drainage of entire continents between different ocean basins, are perhaps the most extraordinary expression of this principle, because they demonstrate, in the most dramatic possible way, how consequential and how absolute the watershed boundary is for the fate of any individual molecule of water that happens to fall on one side or the other. The continental divide of the Americas, which runs along the crest of the Rocky Mountains through North America and continues along the spine of the Andes through South America, is the watershed boundary between the rivers that drain to the Pacific Ocean and the rivers that drain to the Atlantic and the Gulf of Mexico. And at certain points along this divide, the distance between the two drainage basins is so small that a single raindrop falling on a summit ridge would split, one part draining westward toward the Pacific, one part draining eastward toward the Atlantic. The two portions of the same drop of water committed, from the moment of their separation, to journeys of thousands of kilometers in opposite directions, toward ocean basins that have not met since the Atlantic and the Pacific separated as the supercontinent of Pangaea broke apart approximately 200 million years ago. 2 drops of rain, 1 meter apart, 2 different oceans. This is the first thing that rivers teach, that the landscape is divided, invisibly and completely, into drainage systems whose boundaries are absolute, in the way that very few things in the natural world are absolute, and that the fate of any water that falls from the sky is determined, from the moment it touches the ground, by where it has fallen in relation to these invisible boundaries, the geography of the land making a complete and irrevocable decision about where each drop will eventually go before the drop has traveled a single centimeter from its landing point. And within each drainage basin, the water that falls on the landscape does not travel to the river all at once, or all in the same way, or at the same speed. It moves through the catchment by several different pathways, each one operating at its own pace and contributing to the river's flow at different times after the rainfall that produced it, and the particular mix of these pathways in any given catchment determines the character of the river that drains it. Whether the river rises quickly after rainfall or slowly, whether it floods dramatically or moderates its floods through the storage capacity of its soils and its groundwater systems, whether its flow in the dry season is sustained by groundwater discharge or diminishes to a trickle as the shallow water stores that feed it are exhausted. The fastest pathway is overland flow, water that falls on a surface too impermeable or too saturated to absorb it, flowing across the surface directly toward the nearest stream channel in a thin sheet of moving water that the hydrologist calls sheet flow, collecting into tiny rivulets and then small streams as the gradient carries it downhill, contributing to the river's flow within minutes to hours of the rainfall that produced it, and generating the rapid rise of the river level in response to intense or prolonged rainfall that produces flash floods in steep, impermeable catchments. The intermediate pathway is through flow, water that infiltrates into the soil and then moves laterally through the soil profile toward the river channel, traveling through the spaces between soil particles in a movement slow enough to be measured in meters per day rather than kilometers per hour, arriving at the river channel hours to days after the rainfall that produced it, sustaining the river's elevated flow through the days following a storm, even as the overland flow contribution diminishes. And the slowest pathway is groundwater flow, water that percolates downward through the soil profile and into the underlying geological formations, moving through the pore spaces of permeable rock or the fractures of impermeable rock at speeds that range from meters per year to kilometers per century, stored in the aquifer for years or decades or centuries before it eventually emerges at a spring or seeps directly into the river channel from the saturated bank, sustaining the river's low-season flow in the months and years between rainfall events and constituting, in many rivers, the majority of the river's total annual discharge. These 3 pathways operate simultaneously in every catchment in the world, their relative contributions varying with the characteristics of the catchment's soil and geology and vegetation and topography, in ways that give each river its own unique hydrological fingerprint, a characteristic pattern of response to rainfall that reflects the particular combination of soil permeability and geological structure and vegetation cover and catchment shape that the river's drainage basin presents. A river flowing through a catchment of deep, permeable soils overlying porous sandstone will respond to rainfall with a slow, gradual rise sustained over many days, the rainfall moving largely through the soil and the groundwater system before emerging at the river, the flood peaks modest and the low-season flows sustained by the deep groundwater reserves that the permeable geology allows to accumulate. A river flowing through a catchment of shallow, clay-rich soils overlying impermeable granite will respond to the same rainfall with a rapid and dramatic rise, the water unable to penetrate the dense soil surface, running quickly across it as overland flow, the flood peaks sharp and high, and the low season flows brief and depleted as the shallow water stores that fed the rapid response are quickly exhausted. Same rainfall, same volume of water, two entirely different rivers. The sources of the great rivers have occupied the geographical imaginations of explorers and scholars for as long as rivers have had names, and the search for the source of the Nile in particular was one of the defining geographical obsessions of the 19th century, a question whose answer seemed to lie always just beyond the reach of the most recent expedition, the river extending further upstream than any explorer had yet penetrated, its source receding before the advancing knowledge of the century, like a horizon that retreats as you approach it. John Hanning Speke believed he had found the source of the Nile at Lake Victoria in 1858, a conclusion that his companion Richard Burton disputed, and that generated one of the most bitter and most publicly conducted scientific controversies of the Victorian era, Speke dying of a gunshot wound the day before a public debate with Burton on the subject in 1864. A death that was ruled an accident, but that speculation at the time suggested might have been a suicide in the face of the anticipated debate. The question of the Nile's source carrying enough weight in the intellectual culture of the time to constitute, for some of those most invested in its resolution, a matter of genuinely existential significance. The modern consensus places the ultimate source of the Nile at the Ruvenzori River in Burundi, a tributary of the Kagera River that feeds into Lake Victoria, the water that begins its journey there, traveling approximately 6,600 kilometers before reaching the Mediterranean Sea. A journey of roughly 3 months at the river's average current speed, through 10 countries, past some of the oldest continuously occupied landscapes in human history, carrying in its water and its sediment the chemical and biological signatures of every landscape it has passed through and every geological formation it has crossed. The Amazon source was disputed even more recently and more actively than the Nile's, with competing claims from different groups of researchers and explorers generating a geographical controversy that continued into the first decade of the 21st century. The river so vast, and its headwaters so remote and so complex that establishing which of the many tributaries extending furthest from the river's mouth constituted the true main stem required. Satellite-based distance measurements that were simply not available to earlier generations of researchers. The current accepted source of the Amazon is a glacial stream on the slopes of the Mismi volcano in the Peruvian Andes, at an altitude of approximately 5,000 meters above sea level. The water emerging from the melting glacier in a thin, cold, almost unrecognizable trickle that gives no indication of the river it will become by the time it has descended to sea level and gathered the contributions of hundreds of tributaries and crossed the entire breadth of South America. From that Andean glacier to the Atlantic Ocean, the Amazon descends 5,000 meters across approximately 7,000 kilometers, an average gradient so gentle that, in the lower 4,000 kilometers of its course, the river drops less than 1 centimeter per kilometer, a slope so nearly flat that the water moves at walking pace. The river wide and slow and brown, with sediment in its lower reaches, carrying its 11 million years of accumulated sediment load toward the delta, where it has been depositing the mineral wealth of the Andes for as long as it has been flowing. Every river has a story like this, a source that was once unknown and is now located with the precision of satellite technology, a history of human attempts to understand and to reach the beginning of something that has always been in motion, the curiosity about origins that seems to be one of the most deep-seated, and most universal characteristics of the kind of mind that asks questions about rivers in the first place, and every raindrop that falls anywhere in the Amazon's catchment, on the Andean slopes above the glacial source, on the forest canopy of the Brazilian interior, on the flooded savannas of the Pantanal, on the agricultural fields of the Mato Grosso, is already, from the moment it leaves the cloud above it, part of the river, already committed to the river's flow by the geography of the watershed that surrounds it, already beginning the journey that will eventually carry it to the same Atlantic Ocean that all the other drops in the same catchment are also heading toward, each by its own path and at its own pace, together constituting the flow of the largest river on Earth. Allow your breathing to slow now to whatever pace the body finds most comfortable and most easy. The breath finding its own natural gradient the way water finds its natural gradient. Not forced, not directed, simply following the physics of the moment, the diaphragm falling and rising with the same unhurried inevitability that the Amazon falls from the Andes to the Atlantic, step by patient step, meter by gentle meter, in no hurry at all. The river is still flowing. It has been flowing for 11 million years. It will be flowing tonight and tomorrow and through all the quiet years that follow, carrying its ancient water and its ancient sediment and the chemical memory of every rock it has ever touched toward the sea. And as we follow the river downstream from its headwaters, from the glacial trickle on the Andean slope and the spring emerging from the English hillside and the snowmelt stream in the Rocky Mountains, we will discover that the water itself is changing as it travels, that the river is doing something in its journey from source to sea that goes far beyond simply moving water from high ground to low ground, that it is reading the landscape it crosses and recording what it reads in a language so precise and so complete that a single cup of river water, examined carefully enough, tells the story of everything the river has touched since it fell from the sky. The river's memory is what we follow next. Take a glass of water from any river in the world, any river at all, the slow brown, sediment-heavy lower Amazon moving at walking pace through the flat forest of the Brazilian interior, or the cold, clear, fast-moving upper Rhine emerging from its alpine catchment with the particular blue-green transparency of glacially fed water, or a quiet English chalk stream moving through a valley of water meadows in the particular unhurried way of rivers that have been flowing through the same chalk landscape for so long that the landscape and the river have come to resemble each other, each one shaped by the other across the centuries of their coexistence. Hold that glass of water up to whatever light is available, and you will see what appears to be an entirely ordinary and entirely unremarkable substance, water, transparent or slightly colored by the dissolved and suspended materials it carries, perhaps faintly brown with tannins from the forest soils of the catchment, perhaps slightly silty with the fine particles that the current has been carrying in suspension, perhaps perfectly clear in the way of a river that drains a catchment of deep, clean limestone. What you cannot see, what no human eye, unaided by the extraordinary sensitivity of modern analytical chemistry and molecular biology, could ever detect from looking at the water in the glass, is everything else that it contains. The invisible record of every event that has occurred in every square kilometer of the landscape that this river drains, a record so complete and so precise that a scientist equipped with the right instruments and the right analytical techniques could read from that single glass of water the geological history of the catchment's bedrock, the health of the catchment's forests, the agricultural practices of the farmers whose fields drain into the river's tributaries, the presence of specific animal species in remote parts of the catchment that no human observer has visited, And in rivers with long enough records of chemical measurement, the climatic history of the watershed going back centuries, the river remembers everything it has touched. And it has been touching everything in its catchment since the first rain fell on the watershed and the first water began its journey toward the channel. And it has been carrying the chemical record of that touching continuously and without interruption in the same direction toward the sea for as long as the river has been flowing, which in the case of the rivers we have been following is a span of geological time so vast that the accumulated record the river carries is, in its depth and its continuity, unlike any archive that human beings have ever created or could ever create. Begin with the chemistry. Water is, among all the common substances in the natural world, the most effective solvent, the liquid with the greatest capacity to dissolve other substances and carry them in solution, a property that arises from the particular molecular structure of the water molecule, whose slightly asymmetrical charge distribution makes it powerfully attracted to the ions and the polar molecules of the materials it contacts, pulling them from the surfaces of rocks and soils and organic matter and carrying them away in solution with an efficiency that no other naturally occurring liquid approaches. This extraordinary solvent capacity means that water moving through a landscape is continuously dissolving small amounts of everything it contacts, leaching calcium and magnesium ions from limestone, bedrock, dissolving silica from granite, extracting iron and aluminium from the clay minerals of the soil, picking up the organic compounds of the decomposing leaf litter of the forest floor, and the agricultural chemicals applied to the fields of the catchment, and the atmospheric pollutants deposited by rainfall from the air above the catchment, gathering all of these dissolved materials into a chemical cocktail whose precise composition reflects, with extraordinary fidelity, the specific combination of geological and biological and human influences that the river's catchment presents. A river flowing through a limestone catchment has water rich in calcium and bicarbonate ions, the limestone's calcium carbonate dissolving slowly but continuously as the slightly acidic rainwater, made acidic by the carbon dioxide it absorbed from the atmosphere on its way down, contacts the rock surface and reacts with it in the quiet chemical dissolution that has been carving limestone landscapes into their characteristic forms of caves and sinkholes and disappearing streams for as long as slightly acidic water has been falling on carbonate rock. This calcium-rich water has a particular effect on the biology of the river. It buffers the water against acidification, maintains a chemistry favorable to the organisms that build their shells and their exoskeletons from calcium carbonate, supports the growth of the macrophytes and the algae that form the base of the food web of chalk streams and limestone rivers, and gives these rivers the particular clarity and the particular coldness and the particular biological richness that make them, among all the river types of the temperate world, the most consistently productive and the most consistently beautiful. A river flowing through a granite catchment, by contrast, has water much poorer in dissolved minerals, the granite silicate minerals dissolving orders of magnitude more slowly than limestone, the water remaining soft and slightly acid, low in calcium and magnesium, the biological community it supports adapted to these oligotrophic, nutrient-poor conditions in the particular way of organisms that have evolved to thrive in chemical environments that would seem, by the standards of the richly mineralized chalk stream, almost barren. The river's chemistry is a fingerprint of its geology, and a scientist measuring the chemistry of a river at a single point downstream can work backward from those measurements through the known chemistry of the rocks that the river drains. An exercise called inverse modeling in which the measured chemistry of the river water is used to infer the proportion of the flow derived from each geological unit in the catchment, effectively reconstructing the geology of a watershed that the scientist may never have visited from the chemistry of the water flowing past a single monitoring point. The river tells you what it has touched if you know how to ask. But the dissolved minerals are only one layer of the river's memory, and in some respects the least surprising and the least remarkable layer, because the idea that water dissolves things and carries those dissolved materials in solution is intuitive in the way that most chemical ideas are intuitive once they are stated. Of course, water dissolves things. Of course, it carries them downstream. Of course, the chemistry of the water reflects the chemistry of the rocks it has contacted. What is less intuitive and considerably more remarkable is what the river is carrying in its sediment, in the particles of mineral and organic matter that the river holds in suspension in the body of the current, neither dissolved in the water nor settled on the bed, simply suspended in the flow and carried downstream at whatever speed the current maintains, deposited when the current slows below the threshold necessary to keep them suspended, and re-entrained when the current accelerates again, traveling downstream in a stop-and-start pattern of deposition and resuspension that may take a particle of sediment years or decades to complete its journey from the hillside, where it was first, eroded to the delta or the continental shelf, where it will eventually be permanently deposited. The sediment in a river is the physical archive of the catchment's erosional history, a record preserved in the mineral composition and the particle size, and the chemical coating of each individual sediment grain, of where that grain came from, what rock it was eroded from, how long ago the erosion occurred, and what has happened to the grain in the time since it entered the river system. Sediment collected from the bed of the Amazon River and analyzed in the laboratory reveals particles that originated from the Andes. Minerals characteristic of high-altitude igneous and metamorphic rocks that are found nowhere in the lowland Amazon basin, carried thousands of kilometers downstream in the river's suspended load and deposited in the riverbed when the current that was carrying them slowed sufficiently to allow their deposition. The mineral composition of the particle, carrying the geological signature of its Andean origin, as clearly as an address, carries the information of a location. This provenance tracing, the determination of where sediment particles came from, by analyzing their mineral composition and their chemical and isotopic signatures, has become one of the most powerful tools available to geologists studying the erosional history of mountain ranges and the tectonic history of the landscapes that rivers drain, because the sediment archive preserved in river deposits and in the marine sediments of the continental shelves, where rivers deliver their load records across timescales of millions of years, the history of the landscape uplift and erosion that the rivers have been responding to throughout their existence. And then there is the most recent and the most extraordinary layer of the river's memory, a layer whose existence was not suspected until the early years of this century, and whose implications for our understanding of what rivers carry and what they can tell us are still being absorbed and explored by the scientists who discovered it. Environmental DNA. Every living organism, as it goes about its life, sheds genetic material into its surrounding environment. Skin cells, scales, feces, mucus shed hairs or feathers, the microscopic fragments of tissue and secretion that living processes continuously produce and release into the air and the water and the soil of the environment the organism inhabits, each fragment carrying within it the DNA that identifies, with molecular precision, the species from which it came. In an aquatic environment, In a river or a lake or a pond, this environmental DNA, or eDNA as it has come to be called, mixes into the water and is carried by the current in the same way that dissolved chemicals and fine sediment particles are carried, diluted progressively as it moves downstream by the additional water entering from tributaries and from the lateral drainage of the catchment, but remaining detectable by the extraordinary sensitivity of modern DNA sequencing technology at concentrations so low that a single cell's worth of genetic material distributed through hundreds of liters of river water can still be detected and identified. This means that a water sample taken from a river at a single point downstream can be analyzed for eDNA and used to produce a list, not a complete list, not a perfectly quantitative list, but a genuine and scientifically meaningful list of the species present in the river and its surrounding catchment upstream of the sampling point. Each species represented in the sample by the genetic material it has shed into the water, or the lateral drainage that feeds the river carrying the molecular signatures of its biological community, in the same way that it carries the chemical signatures of its geology. Researchers using eDNA analysis have detected the presence of specific fish species in rivers where those species were not known to be present, confirmed the presence of invasive species in river systems before conventional survey methods had detected them, tracked the upstream distribution limits of migratory fish without the need to observe the fish directly, and detected the presence of rare and cryptic species from river water samples alone, effectively reading the biological community of an entire river system from a sample of its water, the river acting as a continuous and automatically updated biological survey system that carries the molecular evidence of everything alive in its catchment past every sampling point in its course. The river is carrying the signatures of every living thing that has touched its water or lived near enough to it to contribute eDNA to its lateral drainage. The fish in the main channel, the mammals that drink from its banks, the birds that wade in its shallows, the amphibians that breed in its backwaters, the insects whose larvae develop in its gravel beds and whose adults emerge from its surface and rest on its bankside vegetation and fall into the current and drift downstream as drift organisms, the whole biological community of the river and its riparian zone represented in the water that flows past any downstream sampling point. The river knows who is home, and it carries that knowledge downstream in the form of molecular signatures, too small to see and too numerous to count, past every point along its course, toward the sea, where the dilution of the marine environment will eventually render the signal undetectable. The river's biological memory dissolving into the ocean, the way all memories eventually dissolve into the vastness of what contains them. Allow your body to grow very still now, in the way that the river grows still in its deep pools, where the current slows and the water holds its depth without any visible motion, the surface smooth and dark and reflecting whatever light the sky above it provides. The river is still flowing. Outside or in the memory or in the imagination, the river is flowing, carrying its dissolved minerals and its suspended sediment and its invisible cargo of environmental DNA downstream toward the sea, recording in its chemistry and its biology the ongoing history of the landscape it drains, updating its archive with every new rainfall that adds new water and new dissolved material to its flow, every new organism that sheds its genetic material into its current, every new geological event in its catchment that releases new sediment into its drainage system. The archive is always current, the river is always writing, and the sediment that the river carries, the mineral particles eroded from the hillsides and the river banks and the catchment soils that form the suspended load of the river's current, will, eventually, when the river slows enough to allow its deposition, become something entirely new and entirely consequential, something that the geological and the human history of the river's floodplain is built upon in the most literal and physical sense. The river's memory, written in sediment, becoming the ground beneath the oldest civilizations on Earth. That is where we go next. The soil that ancient Egyptians called the Black Land was, quite literally, a gift the Nile had been assembling for thousands of years before anyone thought to name it. Every grain of that dark, rich, extraordinarily fertile earth had traveled a long way to arrive there, carried from the Ethiopian highlands, more than 1,000 kilometers upstream, suspended in the flow of the river's annual flood, released only when the flood spread across the valley floor and the current slowed enough to let each particle finally settle, one thin and patient layer at a time, across thousands of years of the same annual event repeating itself with a reliability that no human institution has ever matched. The land did not simply sit beside the river. The land was, in the most direct sense available to geology, made by it. Tonight, in this chapter, we are going to follow the river's sediment to the place where it finally comes to rest. And we are going to understand why the ground beneath some of the oldest and most enduring civilizations in human history is, when you trace its origin carefully enough, simply river. Begin with the physics of settling, because everything about the fertile floodplain begins with a simple and elegant principle of fluid mechanics that governs how a moving current decides what to carry and what to release. A river moving with any given velocity has a corresponding capacity to hold particles in suspension. The faster and more turbulent the flow, the larger and heavier the particles it can keep suspended in the water column, rather than allowing them to settle toward the bed. And the relationship between current speed and particle size is precise enough that hydrologists can calculate for any given flow velocity the largest particle diameter the current is capable of transporting in suspension. When a river is confined to its normal channel, moving with the velocity that the channel's gradient and the volume of water passing through it together produce, it can carry a substantial sediment load in suspension. The fine particles of clay and silt distributed through the turbulent flow and held there by the same turbulence that keeps a spoonful of sugar distributed through a stirred cup of tea. But when the river's volume exceeds what the channel can contain, and the water spreads outward across the floodplain beyond the channel's banks, something changes immediately and completely. The water spreading across the floodplain slows. It slows because the same volume of water is suddenly occupying a much wider area. The flow spreading thin across the flat surface of the floodplain, rather than concentrated within the confines of the channel. And this spreading reduces the velocity of the current dramatically, often by a factor of 10 or more. And this reduction in velocity means the water can no longer hold its sediment load in suspension. The particles begin to settle, the largest and heaviest particles first, near the point where the flood first leaves the channel, and progressively finer particles further out across the floodplain as the current continues to slow, each flood event depositing its own thin layer of sediment across the land it has covered. The coarsest material closest to the channel building the slightly elevated natural embankments that river engineers call levees, and the finest clay particles carried furthest from the channel, settling last in the quiet backwater areas where the floodwater has almost stopped moving at all. Repeat this process every year or every few years across thousands of years, and the floodplain grows, not outward but upward, each flood adding its thin sedimentary layer over the layer the previous flood deposited. The accumulated thickness of these layers building, over the millennia, into the deep and continuous body of fertile alluvial soil that characterizes every great river valley where agricultural civilization first took root. The soil of the Nile Valley is, in places, many meters deep, each meter representing centuries of accumulated flood deposits. Each thin annual layer distinguishable under careful excavation, the way the rings of a very old tree are distinguishable. A stratified record of thousands of individual floods, stacked one atop the other in the patient, an unhurried way that sediment has always accumulated wherever river has been allowed to flood freely, across its natural floodplain. Why is this soil so fertile? The answer lies in what the river has been carrying in that sediment. Because the particles, the flood deposits, are not simply inert mineral grains. They carry with them the nutrients that the river has gathered across its entire catchment. The organic matter eroded from forest soils, the nitrogen and phosphorus and potassium compounds leached from decomposing vegetation, and from the weathering of nutrient-rich rock formations far upstream, all of it concentrated in the fine sediment that settles across the floodplain and renewed freshly with every flood. A field that has been farmed continuously for a single growing season will have its soil nutrients depleted by the crop that has drawn on them, the same way any cultivated soil anywhere in the world loses fertility without some form of replenishment. But a field on a naturally flooding river valley receives that replenishment automatically every year, delivered directly from the accumulated fertility of an entire river catchment that may span hundreds of thousands of square kilometers. The flood functioning as a free and continuous fertilization system whose reliability across the thousands of years before industrial fertilizer existed made the floodplains of the world's great rivers the most consistently productive agricultural land available to any ancient civilization. The relationship between ancient Egypt and the Nile flood was so central to the functioning of the civilization that it shaped the calendar, the taxation system, the religious life, and the entire rhythm of the agricultural year across more than 3,000 years of recorded history. The flood arrived with a seasonal predictability that ancient Egyptian observers tracked with remarkable precision. The rising water measured at structures called nilometers, built at various points along the river, stone or masonry installations with marked scales that allowed officials to record the exact height the flood reached each year, a measurement that carried enormous practical consequence, because the height of the flood was understood to predict, with reasonable reliability, the fertility and the abundance of the harvest that would follow. A flood that rose too little left large areas of the floodplain unwatered and unfertilized, producing a smaller harvest and, in the more severe cases recorded across Egyptian history, genuine famine. A flood that rose too much could damage settlements and infrastructure built too close to the river, the excess water bringing its own kind of hardship even as it promised. For the fields it reached without destroying them, exceptional fertility. Egyptian administrators used the nilometer readings to calculate the agricultural tax obligations for the coming year, well before the harvest itself was gathered. The flood height serving as a genuinely predictive economic indicator in a civilization whose entire material foundation rested on the reliability of this single annual event. This same pattern, a river whose annual flood built and sustained the agricultural fertility of an entire civilization, repeats across the ancient world with a consistency that reflects how fundamental the process is wherever the right combination of climate and topography allows it to occur. The Tigris and Euphrates rivers, flowing through the region historically known as Mesopotamia, deposited the alluvial soils that sustained some of the earliest large-scale agricultural societies in human history. The fertility of the land between these two rivers giving rise to the very name Mesopotamia, a term derived from ancient Greek meaning simply the land between the rivers, the geography itself embedded permanently in the name of the civilization it produced. The Indus River built the alluvial plains that supported the sophisticated urban civilization that developed along its course roughly 5,000 years ago. A civilization whose cities show evidence of remarkably advanced water management infrastructure, reflecting a population that had developed, over generations, an intimate practical understanding of how to live successfully alongside a river whose flood was both the foundation of their agriculture and a force requiring careful and continuous management. The Yangtze and the Yellow River built the alluvial plains of China's earliest agricultural heartlands, each river depositing its own particular sediment across its own particular floodplain and sustaining, across thousands of years, some of the longest continuously farmed agricultural landscapes on Earth. The relationship between these civilizations and their rivers was never simply passive. Ancient farmers across every one of these river valleys developed practices specifically designed to work with the flood rather than against it, timing their planting to follow the flood's retreat so that seeds went into soil that was freshly deposited, freshly fertilized, and freshly moistened all at once, a technique sometimes called flood retreat or recession agriculture, in which crops are sown directly into the wet, nutrient-rich mud left behind as the floodwater withdraws, requiring no irrigation because the soil itself retains sufficient moisture from the flood to sustain the crop through much of its growing period. This technique, refined across countless generations of practical experience long before anyone possessed the scientific vocabulary to explain why it worked, represents one of the most elegant examples of agricultural adaptation to a natural process anywhere in human history. A farming system that required no fertilizer, no irrigation infrastructure beyond what the river provided on its own schedule, and no soil amendment of any kind, because the flood itself performed all of these functions automatically every year as a natural consequence of its own physics. And then, across the 20th century, much of this relationship changed. The construction of large dams on many of the world's great rivers, built for flood control, for irrigation storage, for hydroelectric power generation, each a genuinely valuable engineering achievement addressing genuinely important human needs, had a consequence that was not always fully anticipated at the time of construction. Because a dam does not simply control the timing and the volume of a river's flow, it also traps the sediment. Water flowing into a reservoir behind a dam slows dramatically as it enters the still water impounded by the structure, and this slowing causes the sediment the river had been carrying to settle out within the reservoir itself rather than continuing downstream to be deposited across the floodplain below the dam. The completion of the Aswan High Dam on the Nile in the 1970s brought this consequence into sharp focus for one of history's most studied river systems, because the dam, while providing valuable flood control and water storage benefits, also captured the sediment that had been renewing the fertility of the downstream floodplain for the entire span of Egyptian agricultural history. Farmers who had relied on the annual flood's natural fertilization for millennia found themselves needing to apply manufactured fertilizer to soils that had previously required none, an entirely new agricultural input suddenly necessary to replace a service the river had performed automatically and without cost for as long as Egyptian agriculture had existed. The dam had not made the land less fertile in any permanent sense. The soil that had already accumulated across thousands of years of flooding remained rich, but it had ended the continuous renewal process that had kept that fertility replenished indefinitely, revealing, through the practical consequence of its absence, just how essential the sediment delivery had been to the system all along. There is something worth resting in quietly about this whole story. The river did not build these floodplains quickly, and it did not build them with any intention or any awareness of what it was constructing. It simply moved water downhill, the way water has always moved downhill, and it simply released its sediment load wherever the physics of slowing current dictated that the sediment be released. Grain by grain, flood by flood, across a span of time so long that the resulting landscape came to support some of the largest and longest-lived civilizations our species has ever produced. The river was not trying to build anything. It was simply following the oldest instruction water has ever received. And in following that instruction patiently enough and long enough, it built the ground beneath entire histories. Let your breathing settle now into whatever rhythm feels most natural, the way sediment settles into a floodplain. Not forced, not hurried, simply following the physics of the moment. Each breath finding its own gentle resting place, the way each grain of silt finds its resting place in the slowing current of a spreading flood. The rivers we have been following tonight are still building. Somewhere, right now, a flood is spreading across a floodplain, and somewhere within that spreading water, particles of sediment carried from a hillside hundreds of kilometers upstream are settling toward the ground, adding their thin and patient contribution to a layer of soil that will still be there, richer for their presence, long after tonight has become simply another quiet night in the long accumulated history of the river's work. But the same floods that build such extraordinary fertility can also, when conditions align in a different way, become something the communities living beside the river experience very differently. And understanding why a river's flood is, in ecological terms, not a disaster at all, understanding what actually determines the difference between a flood that renews and a flood that overwhelms, is where we will rest next. There is a word that carries, in ordinary usage, an almost automatic weight of catastrophe: flood. The word arrives, in most minds, already dressed in the imagery of disaster. Submerged streets, damaged homes, the particular anxious urgency of news footage showing rising water, where rising water was not wanted. And this association is understandable, and in the context of human settlement, it is often accurate, because floods genuinely do cause genuine harm to genuine communities, and nothing in this chapter is intended to diminish that reality. But tonight, we are going to set that framing aside for a while, gently, and look at flooding the way a river ecologist looks at it, which is to say, as one of the most ordinary, most essential, and most ecologically productive processes in the entire natural history of a flowing river. In purely ecological terms, a flood is not an anomaly. It is simply the river doing exactly what a river has always done, expanding beyond the boundaries of its normal channel. Whenever the volume of water arriving from its catchment exceeds the capacity of that channel to contain it, spreading outward across the flat, low-lying land that borders the channel, land that the river itself built, across thousands of years of exactly this same spreading and settling process that we followed in the last chapter. Land that exists in the most literal sense, because the river has been visiting it regularly for a very long time. The floodplain is not land that the river has invaded. It is land that belongs to the river in the oldest and most functional sense of belonging. And the plants and the animals and the entire ecological community of a natural floodplain have organized themselves across the deep time of their evolutionary history around the expectation that the river will return to this land regularly, will submerge it periodically, and will withdraw again, leaving behind exactly the kind of enrichment and renewal that we explored in the previous chapter. To understand why some floods are gentle and gradual while others arrive with sudden and dangerous force, we need to understand something hydrologists call the hydrograph, the record, over time, of how a river's water level and discharge rise and fall in response to a rainfall event in its catchment. Every river, for every storm, produces a hydrograph with its own particular shape, and that shape is determined by the physical characteristics of the catchment the rain fell upon. Characteristics we touched on briefly when we discussed the pathways water takes to reach a river, channel, and that we can now follow further into their consequences for flooding specifically. A catchment with steep slopes, thin soils, and sparse vegetation will produce what hydrologists call a flashy hydrograph, a rapid and often dramatic rise in river level within hours of intense rainfall, because the water has nowhere to go except across the surface, unable to infiltrate the thin soil quickly enough to be absorbed, running instead as overland flow directly into the nearest channel, and arriving there in a concentrated pulse that can raise the river's level by several meters within a very short span of time. These are the floods that produce the sudden and genuinely dangerous events, sometimes called flash floods, occurring most commonly in steep mountain catchments, in urban environments where impermeable surfaces like concrete and asphalt have replaced the absorbent soil and vegetation that would otherwise slow the water's journey to the channel, and in arid landscapes where long dry periods have left the soil surface compacted and resistant to infiltration. A catchment with gentle slopes, deep and permeable soils, and extensive vegetation cover produces an entirely different hydrograph, a gradual and sustained rise over days rather than hours. The rainfall absorbed into the soil and moving slowly toward the channel through the through-flow and groundwater pathways we described earlier. The river's level climbing steadily but without the sudden violence of the flashy hydrograph, giving communities and ecosystems alike considerably more time to respond to the rising water. This is why two rivers receiving identical amounts of rainfall can produce dramatically different flooding outcomes. The physical character of the land the rain fell upon determines, to a very significant degree, whether that rainfall arrives at the river as a sudden dangerous pulse or a slow and manageable rise. Hydrologists also describe flood probability using a concept called the recurrence interval, the statistical estimate of how often, on average, a flood of a given magnitude is expected to occur at a particular location based on the historical record of past flows. The so-called 100-year flood is not a flood that occurs exactly once every 100 years on a fixed schedule, a common misunderstanding that deserves gentle correction. It is a flood of a magnitude that has, on average across the historical record, a 1% probability of occurring in any given year, which means that a location can experience 200-year floods in consecutive years purely by chance, or can go 200 years without one, the probability resetting fresh with each new year rather than counting down towards some guaranteed occurrence. This statistical framing helps explain why flood management is fundamentally a science of probability rather than certainty. Engineers and planners working not to eliminate flood risk entirely, which is rarely possible for any river with a large enough catchment, but to manage the probability and the consequences of flooding to an acceptable level, a subtly different and considerably more realistic goal. Within the floodplain itself, the regular rhythm of flooding and retreat creates one of the most biologically rich and most structurally complex habitat types found anywhere in the freshwater world. Ecologists describe this as the flood pulse, the recurring cycle of inundation and drying that characterizes a naturally functioning floodplain. And the biological productivity that this cycle generates is extraordinary because the flood brings with it not only the sediment and nutrients we discussed in the previous chapter, but also a temporary expansion of aquatic habitat into areas that spend the rest of the year as dry or semi-dry land, creating shallow, warm, food-rich water across an enormous area that fish and invertebrates and waterbirds can exploit for the brief season of its existence. Species specifically adapted to this rhythm time their reproduction to coincide with the flood, spawning in the newly inundated grasslands and forests, where their offspring find abundant food and relative shelter from the predators that concentrate in the permanent river channel. And as the flood recedes, these young animals move back toward the main channel, carrying with them the nutritional benefit of a growing season spent in one of the most productive habitat types the floodplain provides. One particularly elegant geomorphological feature that floods regularly produce deserves a slow and careful description because it is among the most visually distinctive landforms that a meandering river creates. As a river winds across a flat floodplain, its meanders, the looping, sinuous curves the channel traces across the land, gradually grow more pronounced over time, the outer bank of each curve eroding while the inner bank accumulates sediment, the loop growing tighter and more extreme with each passing flood season until, eventually, during a particularly large flood, the river may simply cut across the narrow neck of land, separating two parts of the same loop, abandoning the old meander entirely and adopting the new, shorter, straighter path the flood has carved. The old loop, no longer connected to the main flow, becomes an oxbow lake, a crescent-shaped body of still water, cut off from the river's current, that begins its own slow and separate existence, gradually filling with sediment and organic matter across the decades and centuries that follow, evolving from open water to marsh to wet meadow to, eventually, dry land indistinguishable from the surrounding floodplain. The entire transformation unfolding across a timescale of many human generations, a patient and unhurried process of landscape change that the river itself is no longer directly involved in. The abandoned loop simply continuing its own quiet evolution long after the river has moved on to its new course. If rivers have always flooded, and if floodplain ecosystems have always been organized around this rhythm, a natural question arises about the long history of human settlement beside these rivers. Why did people choose, again and again, across every continent and every era of settled agriculture, to build their homes and their fields in places they knew, from repeated experience, would periodically flood? And what did the oldest of these riverside communities understand about living with that rhythm that some of the more recent engineering approaches to flood management have had to relearn? That is where we turn next. For 4,000 years, the communities living along the Yellow River in northern China developed one of the most complex and consequential relationships between any human civilization and any single river system in recorded history. The Yellow River carries an extraordinary sediment load, the highest of any major river on Earth, derived from the vast deposits of a fine, easily eroded soil called loess that blankets the upland plateau through which the river's middle course flows. A soil so readily eroded by both wind and water that the river, across its lower course, has historically carried enough suspended sediment to gradually raise its own riverbed above the level of the surrounding floodplain. This is a genuinely unusual hydrological situation, and it arose from a very long history of human intervention working alongside the river's natural sediment load. As communities built levees to protect farmland and settlements from the river's floods, the river responded, over subsequent centuries, by depositing its sediment within the confined channel rather than across the floodplain, gradually raising the bed of the river within its levee-lined banks until, in places, the river's surface came to sit above the level of the land on either side of it, contained only by the height of the levees themselves. When those levees have failed across the river's long history, the consequences have been severe. the elevated river finding no natural floodplain gradient to spread across, and instead pouring into a landscape sitting below its own bed. And this pattern of catastrophic breach following long periods of confinement is part of why the river earned its historical epithet, sometimes translated as China's sorrow, a name reflecting genuine and repeated hardship across many centuries. And yet, alongside this difficult history of engineering struggle, there is another and quieter story from communities within the same floodplain who developed a fundamentally different relationship with the river's rhythm. Communities that built their settlements on naturally elevated ground within the floodplain, that maintained agricultural practices flexible enough to absorb an occasional flood without catastrophic loss, and that treated the river's periodic flooding not as an enemy to be permanently defeated, but as a recurring condition to be worked around. The same underlying philosophy that shaped the flood retreat agriculture we explored along the Nile. This distinction between working against a river's natural rhythm and working with it has become, in recent decades, one of the central and most actively debated questions in the modern engineering of flood management, and one particular national approach has drawn international attention for the clarity with which it embodies this philosophical shift. In the Netherlands, a country whose entire modern existence has been shaped by an intensive, centuries-long relationship with the management of water, engineers and planners initiated a program in the early years of this century called, in its English translation, Room for the River. The premise of this program represented a genuine departure from the flood management philosophy that had dominated much of the previous century, a philosophy centered on building ever higher and ever stronger levees to permanently exclude the river from as much of its historical floodplain as possible. Instead, the Room for the River approach deliberately returned floodplain land to the rivers it had been taken from, removing selected levees, lowering riverbank elevations in strategic locations, excavating secondary channels that could carry excess flow during high water periods, and relocating some agricultural and residential development away from the most flood-prone areas, all with the explicit goal of giving the river more physical space to safely accommodate the high flows that would otherwise raise water levels dangerously within a narrowly confined channel. The underlying insight driving this approach was a recognition that had emerged from decades of increasingly expensive and increasingly precarious levee reinforcement, that a river confined too tightly for too long tends, eventually, to overwhelm even the most sophisticated engineering designed to contain it, and that accepting periodic, managed, and carefully planned flooding of specific and appropriate land can produce a system considerably safer over the long term than one built entirely around permanent exclusion. This same underlying wisdom appears in less formally engineered form in agricultural traditions that predate modern hydraulic engineering by many centuries. Flood retreat agriculture, the practice of deliberately timing planting to follow a flood's natural recession, sowing crops directly into the freshly deposited and moisture-retentive sediment left behind as the water withdraws, was practiced for millennia. Along the Nile before the construction of modern dams altered that river's natural flood cycle, and similar practices continue today in parts of sub-Saharan Africa along rivers like the Niger and the Senegal, where communities have maintained agricultural systems specifically adapted to the annual rhythm of inundation and retreat, requiring minimal irrigation infrastructure because the flood itself provides both the water and the fertility the crop requires. These systems represent a kind of accumulated practical knowledge, refined across many generations of direct experience with a particular river's behavior, that modern flood engineering has, in some contexts, spent recent decades rediscovering through more formal and more quantitative means. Wetlands play a related and equally important role in this broader picture of natural flood management, functioning as a kind of biological sponge within a river catchment. A healthy wetland, whether a floodplain marsh or an upland bog or a riparian forest with saturated soils, has an extraordinary capacity to absorb and temporarily store floodwater, slowing its passage through the catchment and releasing it gradually over subsequent days and weeks, rather than allowing it to pass directly and rapidly into the main river channel. This buffering effect means that catchments with extensive, intact wetland cover tend to produce more gradual and less severe flood peaks than catchments where wetlands have been drained for agricultural or urban development. The loss of this natural water storage capacity, removing a buffer that had, in many landscapes, been quietly moderating flood behavior for as long as the wetland had existed. Restoring wetlands within a catchment has, in numerous documented cases, measurably reduced downstream flood peaks, offering a form of flood management that works with the existing hydrology of a landscape, rather than attempting to override it entirely with concrete and steel. There is a quiet and consistent thread running through all of this, through the ancient Chinese communities who settled on elevated ground rather than confronting the river directly, through the flood retreat farmers of the Nile and the Niger and the Senegal, through the modern Dutch engineers who chose to give a portion of their carefully managed landscape back to the rivers that had originally shaped it. The thread is this: rivers have always flooded, will always flood, and the communities that have found the most enduring and the most sustainable relationships with their rivers have generally been the ones that accepted this as a permanent feature of the landscape, to be accommodated rather than a problem to be permanently solved. The river is not trying to cause harm when it floods. It is simply following the same patient physics that built the fertile floodplains we explored in the previous chapter. The same overflow of channel capacity that has always, across the entire history of every river on Earth, been the mechanism by which sediment is delivered, nutrients are renewed, and the extraordinary biological productivity of the flood pulse is sustained. Allow your thoughts to settle now, the way water settles into a wetland's absorbent soil, slowing gently rather than stopping abruptly. The transition from motion to stillness, gradual and unforced, the mind releasing its hold on the details of engineering and agriculture, the way the floodwater releases its held sediment, gently, without urgency, simply following the natural tendency of a system moving toward rest. Somewhere tonight, a river is rising gently within its floodplain, exactly as it has risen countless times before, spreading across land that has always expected its return, depositing its patient sediment, nourishing the wetland soils that will, in turn, help buffer the next flood that follows. The rivers we have followed through fertility and flooding, and the long history of human adaptation to their rhythm, are also, we should remember, extraordinary living environments in their own right, home to some of the most remarkable and most specifically adapted organisms found anywhere in the natural world. And in the next chapter, we are going to rest with some of those creatures. Somewhere in a slow-moving river in eastern North America, resting half-buried in the gravel of the riverbed, there is a small and unremarkable-looking animal doing something that, when you first hear it described, sounds less like biology and more like an elaborate and carefully constructed trick. It is a freshwater mussel, and it cannot walk, cannot swim, cannot pursue anything, cannot do any of the things that most animals do when they need something from another living creature. And yet this small, stationary, filter-feeding animal has evolved across millions of years of natural selection, a fleshy extension of its own body that it displays outside its shell, a lure so precisely shaped and so precisely colored that it closely resembles a small fish, or in some species a crayfish, complete with markings that mimic eyes and fins. And the mussel moves this lure gently in the current, with a rhythm that imitates the swimming motion of the animal it resembles. A real fish, the specific host species that this particular mussel's larvae require to complete their development, approaches the lure, drawn by what appears to its senses to be prey or a rival. And in that moment, the mussel releases a cloud of larvae, called glaucidia, into the water directly in front of the investigating fish. And these microscopic larvae attach themselves to the fish's gills, where they will spend several weeks developing, drawing a small amount of nourishment from their temporary host without causing it serious harm, before finally releasing their grip and dropping to the riverbed as fully formed juvenile mussels, ready to begin their own stationary lives, filtering the river water that flows past them. The mussel has, in the most literal sense available to invertebrate biology, built a fishing lure with its own flesh, refined across an evolutionary history so long and so precise that the lure of certain mussel species has come to resemble, with startling specificity, the exact fish species whose gills its larvae require. This is only one of thousands of extraordinary adaptations that rivers, across the deep time of their existence, have shaped into the organisms that depend on them. And tonight we are going to rest slowly with a small handful of these adaptations, moving from the headwaters to the lower reaches the way a river itself moves, each stretch of water home to its own particular community of organisms, fitted with precision to the specific conditions that stretch provides. Freshwater environments, rivers, streams, lakes, and wetlands combined, cover considerably less than 1% of the Earth's total surface area, and yet they support, by conservative estimate, close to 10% of all known animal species on the planet, an extraordinary concentration of biological diversity, packed into a proportionally tiny fraction of the available habitat, a fact that reflects just how many distinct ecological niches a flowing river creates within its relatively narrow physical footprint. A river is not one habitat. It is a sequence of habitats, changing continuously from source to mouth, and ecologists studying rivers have long recognized that the biological community found in the cold, fast, well-oxygenated headwaters of a river is often entirely different from the community found in the warm, slow, sediment-laden lower reaches of the same river system. The two communities separated not by any barrier, but simply by the gradual and continuous change in physical conditions that the river's journey from source to sea naturally produces. In the headwaters, where the water runs cold and fast over stony beds, the organisms that thrive are built for grip and for streamlining. The larvae of certain caddisfly species construct small, portable cases from grains of sand or tiny fragments of plant material. Cemented together with silk, the larva produces itself, a case that serves as both camouflage and physical protection as the larva moves slowly across the streambed, grazing on algae, while other caddisfly species instead spin small, funnel-shaped silk nets anchored to the streambed, positioning themselves downstream of the net's mouth and allowing the current itself to deliver a steady supply of drifting food particles directly into the trap, an elegant solution that requires no active hunting at all, simply patient positioning within a current that is doing the work of gathering food on the animal's behalf. Mayfly larvae in these same fast headwater stretches often have flattened, streamlined bodies specifically shaped to minimize drag and to allow the animal to press itself close against the surface of a stone, reducing the force of the current attempting to sweep it downstream. while gills positioned along the sides of the abdomen extract oxygen efficiently from water that, being cold and turbulent, carries an unusually high dissolved oxygen content compared to warmer, slower water further downstream. As the river widens and slows through its middle reaches, the community shifts again. Fish adapted to this transitional zone tend to have more generalized body shapes than the highly specialized streamlined forms of headwater species, reflecting a habitat with greater variety in current speed and greater diversity in available food sources, from aquatic insects to smaller fish, to the occasional terrestrial insect that has fallen from overhanging vegetation into the water below and in the slow, warm, sediment-rich lower reaches of a great river, the kind of water we have been imagining throughout much of tonight's journey. An entirely different suite of adaptations becomes advantageous. Consider the electric fish of the Amazon basin, a remarkable group of species that have solved a very specific sensory problem presented by their environment. The lower Amazon and many of its tributaries carry such a heavy load of suspended sediment that visibility in the water column can be reduced to only a few centimeters, rendering vision nearly useless for locating food, navigating obstacles, or detecting other animals. And in response to this challenge, several unrelated groups of fish inhabiting these turbid waters have independently evolved the ability to generate weak electric fields around their own bodies and to sense distortions in that field caused by nearby objects. This ability, called electrolocation, allows these fish to build a detailed sensory map of their immediate surroundings using electricity rather than light, detecting the presence, the size, and even something of the internal structure of nearby objects. By reading how those objects distort the electric field the fish itself is continuously generating, an entirely different sensory strategy from the one most animals rely on, evolved specifically because the visual world these fish inhabit offers so little useful information that natural selection favored, across many generations, an alternative and far more effective way of perceiving the environment. Not every remarkable river adaptation involves staying within the river permanently. Some of the most extraordinary river-dependent life histories belong to species that divide their lives between fresh water and the ocean. And among these, the salmon offers one of the most studied and most genuinely remarkable examples in all of vertebrate biology. A salmon begins its life in the cold, gravel-bedded headwaters of a river, hatching from an egg buried in the stream and spending its earliest months or years in fresh water before undergoing a profound physiological transformation called smoltification that reorganizes its body's ability to regulate salt and water balance, preparing it for the transition from the fresh water it was born in to the saltwater ocean environment, where it will spend most of its adult life feeding and growing. Years later, when the biological signal to reproduce arrives, the salmon undertakes the return journey, swimming back from the open ocean toward the coast, and then upstream, against the current, through the same river system it left as a juvenile, navigating using a combination of magnetic field sensing for the open ocean portion of the journey and an extraordinarily precise sense of smell for the final stages. The salmon capable of detecting the unique chemical signature of the specific stream where it hatched, a signature composed of trace minerals and dissolved compounds so particular to that one stretch of water that the fish can distinguish its natal stream from every other tributary in an entire river system, guiding itself home across a journey that may span hundreds or even thousands of kilometers to the precise gravel bed where its own life began. Rest for a moment with the image of a river holding all of this at once, in the same continuous flow, the caddisfly larva anchored in its silk net in the cold headwaters, the electric fish reading its dark and turbid world through invisible fields of electricity in the lower reaches, the salmon somewhere in between, pressing upstream against the current on the final leg of a journey guided by memory encoded in scent. All of it happening simultaneously, all of it sustained by the same continuous body of moving water, each organism fitted with a precision refined across millions of years to the exact conditions the river provides at the exact point in its course where that organism has made its home. And the water carrying all of this life, the water the salmon swims through, the water the electric fish reads with its invisible senses, the water flowing past the mussel's patient lure, is, in itself, something considerably older and considerably stranger than any of the creatures it sustains. That is where we turn next. Here is a thought to rest with slowly, because it is the kind of thought that does not resolve quickly, the kind that the mind needs to be given permission to simply hold, without effort, until it settles into something closer to feeling than to fact. The water in the river tonight, the water carrying the salmon home and feeding the electric fish's invisible senses and settling its patient sediment across the floodplain, is approximately 4.5 billion years old. Not 4.5 billion years since it arrived in this particular river, 4.5 billion years since it first existed as water anywhere at all. The molecules of water on Earth today are, with only very minor exceptions involving the ongoing but exceedingly slow processes of chemical formation and breakdown, the same molecules that have existed on this planet since its earliest formation, arriving here through some combination of processes still actively debated by planetary scientists. Released from the cooling rock of the young Earth itself, delivered by the icy comets and water-bearing asteroids that bombarded the early solar system, or some combination of both. And once that water arrived, it began a journey of continuous circulation that has never stopped. This circulation is called the hydrological cycle, and its most remarkable feature, once you sit with it carefully, is not its complexity but its closure. The Earth is, for practical purposes, a closed system with respect to water. The total quantity of water on this planet has remained approximately constant for roughly 4 billion years, neither increasing nor decreasing in any meaningful way. The same finite volume of water simply moving, continuously and without pause, between the ocean and the atmosphere and the rivers and the ice sheets and the deep groundwater and the bodies of every living thing that has ever existed, cycling and recycling through the same closed loop across the entire span of Earth's biological and geological history. The water molecule that fell as rain on the Ethiopian highlands and is now, weeks later, flowing through the lower Nile toward the Mediterranean has, at some earlier point in its 4.5 billion year existence, very likely been part of the ancient ocean that covered much of the early Earth, has very likely fallen as rain on landscapes that no longer exist in any recognizable form, has very likely been locked for thousands or millions of years within a glacier that has long since melted, has very likely passed through the body of a dinosaur, or a trilobite, or one of the first single-celled organisms that ever lived in the primordial seas. The same water cycling endlessly through every era of the planet's history. Scientists studying the hydrological cycle describe something called residence time, the average length of time a water molecule spends in any particular component of the cycle before moving on to the next stage of its circulation. And the range of these residence times, once you begin to consider them carefully, offers one of the more genuinely vertigo-inducing perspectives available in all of Earth science. A water molecule in the atmosphere, present as vapor or held within a cloud, has an average residence time of only about 9 days before it falls again as precipitation, the atmospheric portion of the cycle moving with a speed that reflects how quickly weather systems form and move and release their moisture. A water molecule in a river has a residence time typically measured in weeks. The water moving from its point of entry into the channel to its eventual arrival at the sea across a span of time determined by the river's length and its average current speed. A water molecule in a lake may remain there for years, or, in the case of very large and slowly draining lakes, for decades or centuries. A water molecule that has percolated deep into groundwater, into the slow-moving aquifers we discussed in earlier chapters, may remain there for centuries or for thousands of years, moving through the pore spaces of rock at a pace so gradual that a single molecule's journey through a deep aquifer system can outlast entire human civilizations. And a water molecule locked within the deep ice of a polar ice sheet may remain there, frozen and motionless, for hundreds of thousands of years. Some of the oldest ice cores ever extracted from Antarctica, containing water that fell as snow more than 800,000 years before the present. Water that has been resting, essentially unchanged, since long before our own species existed in anything resembling its current form. Geologists have discovered water in certain deep and extremely isolated rock formations that appears to have been sealed away from any contact with the surface hydrological cycle for a span of time reaching back not thousands or even millions but billions of years. Ancient brine pockets trapped within rock formations, so deeply buried and so completely isolated that the water within them has had no opportunity to mix with or be renewed by the surface water cycle since a period of the Earth's history so early that it predates the first complex multicellular life. Some of this water, analyzed carefully in laboratory settings, appears to be among the oldest liquid water yet identified anywhere on the planet's surface or near surface, a fragment of the ancient hydrological cycle that simply became isolated, sealed away in stone, continuing to exist in patient and undisturbed stillness, while the rest of the planet's water has continued its endless circulation above it. Set this alongside the ordinary river you have been resting with throughout this documentary, and something interesting happens to your sense of what a river actually is. A river is not simply a body of water moving downhill. It is a temporary and continuously renewed gathering point within a cycle that has been running without interruption for the entire span of the Earth's existence. Every molecule within it carrying a personal history reaching back billions of years, each one having passed through ancient oceans and ancient clouds and ancient ice, and possibly through the bodies of creatures that lived and died long before anything resembling a river valley in its current form ever existed on this particular stretch of land. The hydrogen atoms within every one of those water molecules are themselves considerably older than the water they compose, formed not on Earth at all, but in the first few minutes after the birth of the universe. During the brief and extraordinarily hot period of primordial nucleosynthesis that produced the simplest possible atoms from the raw energy of the Big Bang, and the oxygen atoms, joined to that ancient hydrogen to form each water molecule, were forged later still, inside the nuclear furnace at the core of a star that lived and eventually died, likely in the violent release of a supernova explosion, scattering the oxygen it had spent its lifetime creating out into the surrounding galaxy, where it eventually became part of the cloud of gas and dust from which our own solar system and our own planet and eventually our own rivers would form. The river flowing past you tonight, or the river you are imagining, flowing somewhere in the quiet dark beyond these words, is carrying hydrogen older than the Earth itself and oxygen forged inside the heart of a star that no longer exists, combined into water that has been circulating continuously through this one small planet for 4.5 billion years, passing through oceans and clouds and glaciers and the bodies of countless generations of living things, arriving this particular evening in this particular channel, moving past this particular point in its endless and unhurried circulation. Allow your body to settle very heavily now into whatever surface holds it. The way water settles into the deepest and most patient reaches of the hydrological cycle. The groundwater moving so slowly it seems almost still. The ancient ice holding its stillness for hundreds of thousands of years without any urgency at all. You do not need to hold any of these numbers precisely. Simply let the quality of that age rest somewhere quiet within you. The way age rests within very old stone, present and real, without needing to be measured or fully comprehended. And this same ancient water, cycling endlessly between sky and sea and stone, and every living body it has ever passed through, carries within its continued existence a possibility that reaches far beyond the boundaries of this one small, blue, water-carrying planet. A possibility that the rest of the universe, as far as we currently know, may not share. That is where we rest next. Of all the planets orbiting our sun, only one has rivers flowing on its surface right now. Not rivers that once existed and have long since vanished. Though evidence of those exists elsewhere in our solar system, as we will discover shortly. But rivers actively flowing, tonight, carrying water from higher ground to lower ground in the same continuous gravity-driven motion that every river we have followed through this documentary has always followed. Only Earth, among the 8 planets and the countless smaller bodies orbiting our star, currently has this. For a river to exist and to flow, a planet needs a very particular, and as it turns out, a very rare combination of conditions. It needs liquid water, which requires a surface temperature within a fairly narrow range, warm enough to keep water from freezing solid and cool enough to keep it from boiling away into vapor. It needs enough atmospheric pressure to keep that liquid water stable on the surface at all. Because a surface without sufficient atmospheric pressure will lose its liquid water to sublimation, the direct transition from solid or liquid into vapor, regardless of temperature. And it needs enough topographic variation, enough difference in elevation across its surface to give gravity something to work with, carving channels and establishing the gradients that allow flowing water to move consistently in one direction rather than simply pooling in place. Mars very likely had all 3 of these conditions once billions of years ago. The surface of Mars today is carved with an extensive network of valleys and channels that bear an unmistakable resemblance in their branching patterns and their downslope orientation to the valley networks that rivers carve into landscapes here on Earth. And this resemblance is not coincidental. Planetary geologists studying these features, using orbital imagery and, more recently, direct surface exploration by robotic rovers, have concluded with considerable confidence that liquid water once flowed across the Martian surface, likely for a period spanning hundreds of millions of years in the planet's early history, before Mars lost the thick atmosphere and the warmer climate that had made that flowing water possible. Mars, in other words, once had rivers very much like the ones we have spent this documentary exploring. And then, as the planet's core cooled and its protective magnetic field weakened, the solar wind gradually stripped away much of its atmosphere, and without that atmospheric pressure and the warmth it had helped maintain, the liquid water that had carved those ancient valleys either froze into the subsurface ice, that some of it still exists as today, or was lost to space entirely, evaporating away over a span of geological time too gradual for any single Martian era to have registered the change as anything sudden. The valley networks remain preserved and largely unchanged for billions of years in the thin, dry, current-day Martian atmosphere. a geological memory of rivers that no longer flow, waiting in patient stillness the way a dry riverbed on Earth waits between rainfalls. Except that the rainfall that once filled these particular channels stopped arriving a very long time ago indeed. Further out in the solar system, at Saturn, there is a moon called Titan that offers something even stranger, and in its own way even more beautiful, than the fossil rivers of Mars. Titan has rivers flowing right now, this very night, exactly as Earth does. But they are not rivers of water. Titan's surface temperature hovers around -179 degrees Celsius, far too cold for liquid water to exist in any form except as rock-hard ice. And yet Titan's atmosphere and surface conditions happen to allow a different substance entirely to exist as a liquid at that temperature. Methane, the same simple hydrocarbon that exists as a gas here on Earth, but which on Titan's frigid surface behaves the way water behaves on ours, evaporating from lakes and seas into the atmosphere, forming clouds, falling as rain, and carving river channels and valley networks across the landscape, with a shape and a branching pattern so similar to Earth's rivers that early images returned by the Cassini-Huygens mission left planetary scientists genuinely startled by the resemblance. Titan has river deltas. It has what appear to be dried riverbeds in some regions and actively flowing channels in others. It has an entire methane-based version of the hydrological cycle we explored in the previous chapter: evaporation and condensation and precipitation and river flow and eventual return to a sea. The same fundamental physics of fluid moving under gravity playing out on the icy surface of a distant moon, using an entirely different chemistry to produce landscapes that look, to any eye trained on Earth's own rivers, remarkably and eerily familiar. Beyond Titan and Mars, planetary scientists have identified other locations in our solar system where liquid water may exist today, though not as rivers flowing openly across a surface. Europa, one of the large moons orbiting Jupiter, appears from gravitational and magnetic field measurements to harbor a vast ocean of liquid water beneath its icy outer shell, kept liquid not by warmth from a distant sun, but by the flexing and internal heating produced as Jupiter's powerful gravity tugs on Europa's interior during its orbit, generating enough friction and heat to maintain liquid water far below a frozen surface that may be tens of kilometers thick. Enceladus, a much smaller moon of Saturn, shows even more direct evidence of a subsurface ocean, in the form of dramatic plumes of water vapor and ice particles that erupt from cracks near its south pole, spraying material out into space in a way that has allowed spacecraft to fly directly through these plumes and sample their chemistry, revealing the presence of salts and organic molecules within the hidden ocean below. The search for liquid water elsewhere in the solar system and beyond carries a significance that goes well beyond simple planetary curiosity, because every environment on Earth where liquid water is reliably present, no matter how extreme the surrounding conditions, has been found to host some form of life, a pattern so consistent across the deep ocean vents and the underground aquifers and the ice-covered polar lakes of our own planet that many astrobiologists treat the presence of liquid water as one of the single most important indicators of where life might plausibly be found elsewhere. This is not a guarantee. Liquid water alone does not create life, and there are almost certainly many additional and more subtle conditions required for life to actually emerge and persist somewhere. But water appears to be, as far as our current understanding extends, a necessary foundation, and its presence or absence on other worlds remains one of the most actively investigated questions in all of contemporary planetary science. Every mission sent to Mars or to the icy moons of the outer solar system carrying, among its various scientific goals, some version of this same underlying question. There is something worth resting with in the fact that flowing rivers, in the specific and familiar sense we have spent this entire documentary exploring, appeared to be genuinely rare across the worlds we have so far been able to study closely. Rivers require an unusually precise and unusually stable combination of temperature, pressure, and topography, sustained not for a brief geological moment, but across spans of time long enough for the slow processes of erosion and sediment deposition and ecological adaptation to unfold. Long enough for a mussel to evolve a lure resembling a fish, long enough for a salmon to develop the extraordinary sensory precision required to find its way home across an entire ocean. Earth has maintained these conditions with relative stability for billions of years, and across nearly every culture and every era of human history, rivers have carried a symbolic weight in human thought and storytelling that seems to echo something genuinely true about their role in sustaining everything that depends on them, appearing again and again as images of life, of continuity, of time moving steadily and irreversibly forward. A symbolism so consistent across otherwise very different human traditions that it may simply reflect an accurate intuition, arrived at independently and repeatedly across our species' history, about the deep and fundamental relationship between flowing fresh water and the very possibility of a living world. Let your breathing settle now into whatever rhythm feels most natural. The way Titan's methane rivers settle into their frozen valleys. The way Europa's hidden ocean rests quietly beneath its shell of ice, patient and undisturbed, needing nothing from the universe around it, except the continued and reliable presence of the conditions that allow it to remain exactly as it is. Earth still has its rivers, tonight and for a very long time still to come. And now, gently, we are going to leave the science behind entirely and simply rest beside one. There is nothing left to explain now. No more chemistry, no more geology, no more distant moons or ancient sediment or 10,000-year floods, simply the river. It is dark now. Wherever this river is, the water moves the way it has always moved, following the same gentle gradient it has followed for longer than there has been anyone beside it to notice. Somewhere upstream, the current passes over smooth stones, and the sound it makes is soft and low and endlessly repeating, never quite the same from one moment to the next, and yet never really changing at all. The moonlight, if there is moonlight tonight, rests on the surface of the water in long, broken lines, shifting gently as the current moves beneath them, the light and the water working together the way they have always worked together, without any need for an audience. The banks are quiet. Somewhere nearby, a single sound, a small splash, a soft rustle in the reeds, and then nothing again, just the water moving. The river does not know that you are listening. It does not know anything at all, in the way that a person knows things. It simply continues, the way it has always continued, carrying its ancient water toward the sea, patient, unhurried, indifferent to the hour. Somewhere far upstream, a single drop of rain that fell days ago is still making its way down, through soil, through stone, into a stream, into this river, adding itself quietly to everything already here. Somewhere far downstream, the water that passed this point an hour ago is already reaching the wide, slow stretches near the sea, still carrying, faintly, the memory of everywhere it has been. The night is very still, the water is very old, and it is simply here now, moving past you in the dark, the way it always has. You do not need to think about any of it any longer, just the sound, just the water. Just the slow, unhurried current, carrying everything it has ever known toward a sea that has been waiting for it since before there were rivers at all. Rest now. The river will still be here when you wake. It always is. Epilogue. The river, continuing, we have traveled a long way tonight. From the single raindrop landing on an invisible line, somewhere high in a mountain range, already committed, from that first moment of contact with the ground, to one ocean rather than another, through the river's memory, its chemistry, its sediment, the quiet molecular traces of every living thing that has touched its water, through the fertile black soil that a river built, grain by grain, across thousands of years, and the civilizations that rose from that patient work, without ever fully realizing how much of their world had been assembled by moving water, through the physics of a flood, which is not a disaster in the eyes of the river itself, but simply the river remembering, once again, the full width of the land that has always belonged to it, through the ancient wisdom of communities who learned, long before any engineering textbook existed, to live beside a river by moving with its rhythm rather than against it, through the mussel with its small and patient lure, and the salmon finding its way home by scent across an entire ocean, and the electric fish reading a world too dark for any eye to see, through water older than the earth itself, hydrogen born in the very first moments after the universe began, oxygen forged in the heart of a star that no longer exists, carried together for 4.5 billion years in an endless and unbroken circulation, and through the quiet, distant possibility of other rivers on other worlds, flowing in methane instead of water, or hidden entirely beneath shells of ice, waiting to be found. None of that needs to be held on to now. You do not need to remember the numbers, or the names, or the order in which any of it was said. Simply let it settle, the way sediment settles when a current finally slows enough to let it rest. The river is still out there somewhere. It was flowing before this documentary began, and it is flowing now, and it will still be flowing when this documentary ends, and it will still be flowing tomorrow, and next year, and in 100 years, long after tonight has become nothing more than one small, quiet night among the millions of nights the river has already passed beneath. It does not need you to listen. It never has. It simply continues, the way it has always continued, following the same patient gradient, carrying the same ancient water, moving steadily toward a sea that has been waiting, without any impatience at all, since long before there were rivers to reach it. Somewhere upstream right now, rain that fell days ago is still making its way down through soil and stone, gathering into some small and nameless stream. Somewhere downstream right now, water that has been traveling for weeks is spreading out into the wide, unhurried calm where a river finally meets the sea, releasing at last the sediment it has carried so far. And everywhere in between, the river simply moves the way it always has. Let your own breathing settle into that same rhythm now, slow and steady, and entirely without effort. Each breath arriving and releasing the way each small wave arrives and releases against a quiet bank. There is nothing left to explain. There is nothing left to understand. There is only the water moving gently through the dark, patient, ancient, and completely at peace with how long everything takes. The river will still be here when you wake. It always is. Rest now. Simply rest. And let the river carry the rest of the night for you. Good night, Da.